largest ship in the world doesn't just transport goods, it bends 48,000 tons of steel to its will. In the middle of a restless ocean, where a 1-degree misalignment isn't just an error, it's a multi-million-dollar catastrophe. Engineers are performing a high-stakes industrial ballet. Today we go inside the firing line of the pioneering Spirit to see how the unmovable is moved. To understand the sheer efficiency of this vessel, we have to look at how it processes raw material. The journey begins with 12-meter single-pipe joints delivered by supply ships. At sea, laying a pipe is a continuous manufacturing process. The first challenge is doubling the speed. To do this, All Seas uses a double jointing factory within the ship itself. Two 12-meter joints are cleaned and preheated. Then, the proprietary Phoenix automatic welding system takes over. This system performs a simultaneous internal and external fusion to create a single 24-meter section. This extra step effectively doubles the ship's daily progress because every weld completed here is one less needed on the main production line. But speed means nothing without integrity. Every weld is subjected to rigorous ultrasonic testing. Under the immense pressure of the deep sea, the smallest microscopic flaw in a weld could lead to a pipe burst, causing an environmental disaster. Once verified, the joints are coated with anti-corrosion protection and lowered into the firing line. Here, the 24-meter pipes are joined to the main line, already descending into the abyss. The ship must maintain constant tension. If the pipe is too loose, it buckles, too tight, and it snaps. This balance is managed by a massive ramp called the stinger, which guides the steel into a precise S-curve as it transitions from the ship's deck to the seabed. The scale of this operation is hard to overstate. We are talking about miles of steel pipe, each section weighing tons, being welded and deployed while the ship moves forward at a steady crawl. It requires perfect synchronization between the welding stations, the tensioners, and the vessel's propulsion. This is not just construction. It is a moving assembly line fighting against the unpredictable forces of the North Sea, proving that even the most massive engineering challenges can be solved through precise, repetitive excellence. Moving from pipelines to power infrastructure, we encounter the Dalwin-Kappa project. The goal: install a 900-megawatt converter station in the German North Sea. But this isn't just a platform. It's a 10-story industrial building weighing 10,000 tons. The hardest part of this operation is the stability. The station was transported over 690 kilometers of open water. During the journey, the primary enemy is the sea's movement. Even a slight roll of the transport barge can put immense stress on the structure's sensitive electronics. Once at the site, the installation depends entirely on the ship's dynamic positioning system. Using satellites and high-powered underwater thrusters, the vessel must hold its coordinates with millimeter precision. As the heavy lift cranes lower the topside onto its pre-installed jacket, the tolerance is nearly zero. Engineers call this mating. If the ship moves more than a few inches due to a wave, the 10,000-ton structure could collide with the support legs, causing catastrophic failure. By successfully lowering this giant, engineers have effectively built a bridge that will transmit clean energy to over 1 million homes. It is a triumph of logistics and maritime precision, where the weight of a skyscraper is managed with the delicacy of a watchmaker. The Dalwin 6 project represents a critical link in the global transition to renewable energy. While wind turbines capture the power, it is the converter station that makes that power usable for the mainland. The technical problem solved here is one of physics: electrical loss. When transmitting electricity over long distances subsea, standard alternating current loses a significant amount of its energy. To solve this, engineers use high-voltage direct current, or HVDC. The Dalwin 6 station acts as a massive converter, taking the raw power from offshore wind farms and transforming it into DC for its 90-kilometer journey through subsea cables. Building such a system in the middle of the ocean requires extreme engineering redundancy. Every transformer, pump, and circuit breaker inside this structure must be designed to withstand constant vibration in salt-laden air. The logistical scale is equally daunting. From the fabrication yard to the offshore site, every stage is a race against weather windows. During the installation phase, the project uses a heavy lift method. The coordination between the transport barge and the installation vessel is handled by a command center, where real-time data from wave sensors and GPS dictates every move. The complexity continues with the connection of the export cables. These are not simple wires, they are armored giants that must be pulled through J-tubes on the jacket structure and connected to the high-voltage switchgear inside the station. This requires specialized teams working in cramped conditions, ensuring every connection is secure against the elements. A single mistake during this process doesn't just delay the project, it puts billions of dollars of infrastructure at risk. Dalwin 6 is a testament to the fact that we can now build complex industrial hubs in the most hostile environments on Earth, providing a blueprint for the future of the global energy grid. It shows that the bridge to a sustainable future is built with heavy steel and advanced electrical engineering. In offshore engineering, the invisible work is often the most important. In the Mariner project, that work involves the jacket, a steel lattice foundation weighing 1,240 tons. Lowering this massive frame into the North Sea is a delicate operation, but the real challenge begins once it touches the seabed. To ensure the platform remains stable against 100-foot waves for the next 50 years, it must be anchored into the Earth itself. Engineers use a massive 800-ton hydraulic hammer to drive 8 steel piles 55 meters deep into the ocean floor. This is a brutal display of industrial force, but it is driven by precise data. Sensors on the hammer monitor soil resistance in real time. If the soil is softer than expected, the piles must go deeper. Once the foundation is locked, subsea metrology, underwater laser measurement, is used to map the site. This ensures that when the pipelines are eventually connected, the fit is perfect down to the millimeter. The Mariner project proves that before you can build a giant on the surface, you must first conquer the ground beneath the waves. Before we can lay a single mile of cable across the seafloor, we must understand the engineering required to protect it. At the Hellenic Cables facility, the process begins with the core. These aren't just wires. They are high-precision conductors of massive energy. The copper or aluminum core is shielded by multiple layers of insulation, lead sheathing, and galvanized steel armoring. Why so much protection? Because once submerged, this cable must resist the corrosive power of salt water and the immense crushing weight of the deep ocean. Any breach in these layers would mean an immediate short circuit, cutting off power to entire regions. We see the vertical laying process here, where cables are wound into massive turntables, often weighing thousands of tons. This manufacturing stage is where the battle against the elements is won or lost. Every meter is tested for electrical integrity, ensuring that these subsea veins can pulse with energy for half a century without fail. While inter-array cables connect turbines, the export cable is the massive artery that carries the entire wind farm's power back to the mainland. In the Galloper project, Boskalis demonstrates the complexity of the landfall operation. This is where the deep-sea cable must transition from the vessel to the shallow waters near the coast. The operation begins by floating the cable toward the shore using a series of high-buoyancy floats. Large winches on the beach pull the cable through pre-drilled conduits, often extending hundreds of meters under the seabed to avoid disturbing the sensitive coastline. This horizontal directional drilling method ensures the cable is buried deep before it even touches the water. Once the shore end is secured, the vessel begins its journey offshore. The hardest part of this installation is the weight management. Export cables are significantly larger and heavier than internal array cables, requiring massive carousels and high-tension engines to control the descent. As the ship moves, it must maintain a perfect heading to stay within the narrow environmental corridor. Any deviation could lead to the cable being laid over rocky outcrops or existing pipelines, which would require a costly and difficult relocation. The Galloper installation highlights the bridge between two worlds, the extreme conditions of the offshore field and the fixed infrastructure of the electrical grid on land. Every mile of this cable is a testament to the logistical coordination required to bring renewable energy from the wind to the consumer. The NKT high-voltage cable system represents a complete turnkey solution, bridging the gap between factory production and offshore reality. The scale of the logistics is staggering. The cable is fed directly from the factory into the belly of specialized cable-laying vessels. These ships are equipped with massive carousels that maintain the cable's bend radius. If the cable bends too sharply, the internal insulation will crack, rendering the entire length useless. As the vessel moves offshore, the installation process becomes a game of constant tension and precise navigation. Using advanced tensioner systems, the ship controls the descent of the cable to the seabed. It's not just about dropping a line, it's about managing the touchdown point. If the cable is laid too loosely, it creates loops that can snag on anchors. Too tight, and it risks snapping under its own weight. The ship's dynamic positioning system works in tandem with the cable engine to ensure the layout follows the pre-surveyed route with centimeter precision. This is where we see the convergence of heavy mechanical power and delicate sensor data. Every mile of cable laid is a victory for offshore connectivity, turning the ocean floor into a global energy highway. The Nordsee One project offers a clear look at the final stage of subsea connectivity, the actual installation of inter-array cables. In the turbulent waters of the German Bight, the vessel must execute a high-precision maneuver to bring the cable from the seabed into the turbine's transition piece. This process begins with a pull-in operation, where a powerful winch on the turbine deck pulls the cable through a protected J-tube. The primary technical challenge here is managing the bend radius. High-voltage cables are stiff and heavy. If they are bent too sharply during the pull-in, the internal insulation will fail, creating a weak point that could lead to an electrical blowout later. To prevent this, engineers use articulated pipe protectors that guide the cable into its final position. Once the cable is secured inside the turbine, the vessel moves forward, carefully laying the line along a pre-surveyed path toward the offshore substation. It is a slow, methodical process where every meter of cable is tracked by subsea sensors to ensure it sits perfectly on the seafloor, ready to be buried and protected from the elements. At the McDermott Spool base, we see the industrial heart of offshore pipe-laying logistics. This facility acts as a staging ground where miles of steel pipe are welded together into continuous strings before being spooled onto massive reels. The sheer scale of the LV-105 vessel, shown here, is a testament to the weight these ships must carry. Unlike the pioneering Spirit, which welds as it moves, reel-lay vessels like the LV-105 carry pre-welded pipelines, allowing for much faster installation speeds once they reach the field. The spooling process itself is a delicate operation. The steel pipe is literally bent around a giant drum, a process that requires the steel to have high ductility to survive the plastic deformation without cracking. Once offshore, the pipe is unspooled and straightened before being lowered into the water. This method is highly efficient for smaller diameter pipes and umbilicals, reducing the time spent in dangerous weather windows. It highlights the importance of the onshore-offshore link. The better the preparation at the spool base, the safer and faster the operation becomes in the unpredictable open sea. The Reckon project is a masterclass in offshore energy synchronization, representing a full-scale industrial effort to link deep-sea resources with onshore infrastructure. This operation isn't defined by a single machine, but by the seamless integration of mooring towers, subsea pipelines, and floating storage units. The journey begins at the fabrication yard, where the mooring tower is constructed. This is a massive steel structure designed to be the central nervous system for offshore loading operations. Once completed, it is transported over 690 kilometers on a specialized barge, a journey where the structural integrity is constantly monitored against the stress of open ocean transit. Upon arrival at the field, the first major technical challenge is the installation of the jacket foundation. Similar to what we've seen in the North Sea, this 1,240-ton lattice frame is lowered to the seabed using a heavy lift crane. But placement is only the beginning. To ensure this tower can withstand hurricane-force winds and the constant pull of a 100,000-ton tanker, it must be anchored with absolute permanence. Engineers deploy an 800-ton hydraulic hammer to drive 8 massive steel piles 55 meters into the ocean floor. Each blow of the hammer provides critical data. If the soil resistance doesn't meet the engineering models, the piles must go deeper. This is the brutal force required to create stability in a liquid environment. With the foundation secured, the focus shifts to the subsea arteries, the pipelines. These lines are the connection between the mooring hub and the refineries. The installation process uses a sleigh method where the pipe is welded on the vessel and guided to the seafloor. The most complex part of this stage is the subsea tie-in. The pipeline must meet the tower's base with millimeter precision at depths where visibility is near zero. To achieve this, the team utilizes subsea metrology, using acoustic sensors and laser scanning to create a 3D map of the seabed. This data allows for the custom fabrication of spools, or connector pipes, that bridge the final gap between the main line and the tower's intake manifold. As we move to the upper sections, the project enters its most delicate phase, the installation of the 1,000-ton topside module. This unit contains the control systems, swivel stacks, and safety valves that manage the flow of oil. Landing this module onto the jacket requires the vessel's dynamic positioning system to fight against currents while the crane performs the final drop. Once the topside is locked, the team begins the connection of the jumper hoses. These are flexible, high-pressure conduits that allow the floating storage and offloading unit, or FSO, to move freely with the tides while remaining connected to the fixed tower. These hoses must be durable enough to survive constant mechanical stress and the corrosive nature of the hydrocarbons they carry. The final stage is the integration of the control umbilicals. These specialized cables provide the power and data link required to monitor the entire system from a remote center. Every sensor on the mooring tower, from pressure gauges to leak detectors, is connected back through these lines. The Raken project proves that offshore engineering is an interdependent chain. A single failed weld in the pipeline or a misaligned pile in the foundation could halt the entire energy supply chain. By the time the first tanker moors to the tower, years of extreme logistics and high-pressure engineering have converged into a single, resilient system. It is a testament to human ingenuity's ability to build permanent hubs in the most unpredictable environments on the planet, ensuring that energy flows safely from the depths of the ocean to the world above. The veins of the ocean are now laid, and the energy has begun its journey through thousands of miles of steel and copper. But as we move further from the surface, the environment becomes too hostile for any human to intervene directly. To maintain this hidden world, we must rely on a different kind of worker. In the next chapter, we descend into the abyss to meet the silent, autonomous machines that operate where the pressure is high enough to crush a submarine. As we move from the surface to the subsea environment, the first challenge is visibility. Engineers need a way to monitor the cable's touchdown point in real time, often in high currents. This is where the cable fish system comes in. The launch process utilizes a specialized electric davit crane. Unlike standard cranes, this system must manage the umbilical, the cable's data and power link, without interfering with the main power cable being laid. The launch requires perfect synchronization. As the davit crane swings the cable fish over the side, tension sensors monitor the load to prevent any sudden jerks that could snap the fiber optics inside. Once the device hits the water, it travels down the main cable like a sliding sensor pod. The electric winch on the crane adjusts the depth based on the vessel's speed. This allows operators on the bridge to see exactly how the cable is behaving as it approaches the seabed. It is the eye of the operation, providing the visual data needed to adjust the ship's dynamic positioning. Without this precise launch and recovery system, laying cable in deep water would be a blind and dangerous gamble. Having a clear view of the seafloor is vital, but the ocean floor is rarely a smooth surface. To protect these lifelines from the dangers of the deep, we need something more than just cameras. We need brute mechanical force. This demonstration of the cablefish system highlights why visual confirmation is a game changer for subsea logistics. In traditional cable laying, engineers rely on tension data and mathematical models to guess where the cable hits the seafloor. Cablefish removes the guesswork. By riding directly on the cable, it provides a stable, close-up view of the touchdown point, regardless of water depth or turbidity. The high-definition cameras and powerful LED lights allow the bridge team to spot obstacles, rocky outcrops, or existing pipelines that weren't captured in the initial survey. This real-time feedback loop allows for immediate course corrections, significantly reducing the risk of cable suspension or free spanning, where a cable hangs between 2 points and becomes vulnerable to fatigue. The precision offered by cablefish doesn't just make the installation faster, it makes the final infrastructure far more durable. It represents the shift from manual estimation to digital certainty in the world's most challenging construction environment. The LD Travotion TM05 is a subsea monster designed for one purpose: protecting the veins of the ocean. Once a cable is laid, it is vulnerable to ship anchors and deep-sea currents. The TM05 solves this by digging a protective trench while the cable is fed through its internal guide. What makes the TM05 remarkable is that it is a diverless system. It operates at depths where the pressure would crush a human being instantly. The machine uses a combination of high-powered water jets and mechanical chain cutters to slice through the seabed. Its massive tracks allow it to navigate uneven terrain, while a suite of onboard sensors sends real-time telemetry back to the surface ship. Operators use joysticks to control the machine, watching through multiple cameras as the TM05 carves a path and buries the cable in a single pass. The challenge here is the soil consistency. If the machine hits a rock, it must adjust its torque and water pressure instantly to avoid damaging the cable or getting stuck. The TM05 is essentially a submarine bulldozer, powered by thousands of volts and controlled through miles of umbilical cable. It provides the final layer of security for offshore infrastructure, ensuring that the connection remains undisturbed for decades. Watching this machine crawl across the lightless seafloor is a reminder of how far offshore engineering has come, replacing human danger with mechanical precision. Every foot of trench it digs is a safeguard for the world's power and data networks. While some machines are built to dig, others are designed for surgical precision. In the most complex gas fields, the challenge isn't just depth, it's managing the delicate balance of fluids and power in a single line. In the Kiranskoy field, the Jan de Nul group demonstrates the precision required for umbilical installation. An umbilical is the lifeline of a subsea well, carrying hydraulic fluids, chemicals, and high-voltage electricity in a single bundle. Because these lines are more delicate than standard pipelines, the installation requires a constant, steady tension provided by the vessel's vertical lay system. Every meter is monitored to ensure the bundle doesn't twist or kink, which would permanently block the vital fluid lines inside. This operation highlights the transition from brute force to technical finesse, as the vessel must hold a perfect station above the subsea template while the umbilical is lowered into its final connection point. It is the final, critical link that brings a subsea field to life, operating thousands of feet below the freezing waters of the Sea of Okhotsk. The installation of power cables between Ras Laffan and Halul Island presents a different set of challenges: high temperatures and complex seabed morphology. In this project, the Jan de Nul group utilized specialized cable-laying vessels equipped with high-capacity carousels to manage the long-distance transmission lines. The process begins with a meticulous shore-end pull, where the cable is floated onto the beach using a series of buoys before being anchored at the substation. As the ship moves into deeper water, the focus shifts to seabed protection. In areas with rocky terrain or heavy shipping traffic, laying the cable on the surface is not an option. The crew must coordinate the cable deployment with subsea burial tools to ensure the line is tucked safely beneath the seabed. This requires constant communication between the deck crew, managing the tensioners, and the ROV pilots monitoring the trenching progress. The Arabian Gulf seabed can be unpredictable, with shifting sands and sudden limestone formations that test the limits of the cutting equipment. Precision navigation is critical here, as the cable must follow a strictly defined corridor to avoid existing oil and gas infrastructure. Every movement of the vessel is dictated by GPS data and real-time sonar mapping. By successfully linking the mainland to Halul Island, engineers are not just providing power, they are securing the energy independence of vital offshore facilities. It is a massive logistical puzzle where hundreds of variables must be managed simultaneously to ensure the cable remains intact and functional for its 30-year lifespan. This project exemplifies how localized environmental challenges dictate the choice of machinery and the rhythm of the installation process. To see how all these elements, logistics, precision, and brute force, come together in one massive project, we must follow the journey of the SNA from the harbor to the heart of the Atlantic. The SNA project begins at the industrial heart of the operation, the Saint-Nazaire harbor. Here we see the logistical complexity of handling inter-array cables before they ever touch the water. Thousands of tons of cable are delivered on massive transport reels, requiring specialized heavy-lift cranes for the unloading process. This is a critical moment where the cable is most vulnerable to mechanical damage. If the reel is dropped or the cable is bent beyond its minimum radius during the transfer, the internal insulation could be compromised, leading to a failure that might not be detected until the cable is energized months later. Engineers monitor the spooling process with high-precision sensors, ensuring that every kilometer of cable is accounted for and stored in a controlled environment. This mobilization phase is the foundation of the entire project's success. Mobilization is the process of transforming a vessel into a specialized offshore factory. For the SNA project, the cable-laying vessel, CLV, must be equipped with a massive internal carousel capable of holding hundreds of kilometers of cable. This isn't just about loading weight, it's about balancing the ship's stability and ensuring the cable can be fed out smoothly during installation. During the first port call in July 2021, the final technical checks are performed. Engineers calibrate the tensioners, the machines that grip the cable and control its speed, and test the ROVs that will serve as the ship's eyes on the seafloor. The primary problem solved during mobilization is the integration of multiple systems. The ship's navigation, the cable engine, and the burial tools must all work as a single, synchronized unit. Any software glitch or mechanical misalignment found here would be a disaster once the ship is hundreds of miles offshore. This stage also involves the complex loading of cable protection systems, the heavy, articulated shells that prevent the cable from wearing down against the turbine foundations. By the time the vessel leaves the harbor, it is no longer just a ship. It is a high-tech platform ready to fight the currents of the Atlantic. The readiness of the crew and the precision of the equipment during this phase are what make the difference between a successful installation and a multi-million-dollar delay. Summer 2022 marks the execution phase of the SNA project, the offshore installation of the inter-array cables. This is where the preparation meets the reality of the open sea. The vessel must navigate to each wind turbine foundation, maintaining its position within a few centimeters using dynamic positioning. The process begins with the pull-in operation. A messenger wire is sent down to the seabed, attached to the cable end, and winched up into the turbine's transition piece. The hardest part of this stage is managing the cable's entry into the J-tube, a curved pipe that protects the cable as it rises from the seabed. If the cable isn't aligned perfectly, it can jam or become damaged against the steel edges. On the seabed, the cable is laid along a pre-surveyed path toward the next turbine. Here we see the cable protection systems being deployed to ensure the cable doesn't chafe against the rocky Atlantic floor. Every move is watched by ROVs, providing a live feed of the touchdown point to the operators on the bridge. The rhythm is relentless. Pull in, lay, protect, and move to the next. This cycle continues 24 hours a day, capitalizing on the calm summer weather windows. It is a grueling test of human endurance and mechanical reliability as the team works to weave the subsea web that will bring the wind farm's power to life. The overall SNA project provides a comprehensive look at the life cycle of offshore wind infrastructure. From the initial transport of raw cables to the final energized connection, every step is a masterclass in risk management. We see the transition from the heavy industrial setting of the harbor to the high-tech environment of the offshore field. The project highlights the necessity of diverse machinery, from the heavy lift cranes in Saint-Nazaire to the precision ROVs on the seabed. One of the most impressive aspects of the SNA project is the scale of the data involved. Every centimeter of cable is tracked, every weld is logged, and every seabed survey is mapped in 3D. This ensures that if a fault occurs years from now, engineers will know exactly where the cable is buried and what the soil conditions were at the time of installation. The successful completion of the inter-array network represents more than just a construction milestone. It is the realization of a sustainable energy hub. Thousands of man-hours and millions of dollars in technology have converged to create a system that is almost entirely invisible to the world above. This is the hallmark of modern offshore engineering. The most complex work happens out of sight, deep within the ocean, providing a silent foundation for the energy transition. As the final cable is buried, the project stands as a testament to human ingenuity's ability to conquer the most hostile environments on our planet. The subsea web is now active, maintained by a silent army of machines that never sleep. But as the world's hunger for energy and data grows, engineers are no longer satisfied with just laying cables on the seafloor. We are now pushing into the final frontier, turning the deep ocean into a place for permanent habitation, massive data storage, and the extraction of rare resources from the abyss. In our final chapter, we look at the future, the subsea frontier. For decades, the biggest cost for data centers has been cooling. Microsoft's Project Natick solves this by moving the cloud into the ocean. This undersea data center is a self-contained, pressurized steel vessel housing hundreds of servers. The engineering logic is simple. The deep ocean provides a consistent, natural heat sink, allowing for highly efficient cooling without the need for massive air conditioning units on land. However, the hardest part is reliability. Unlike a land-based facility, you cannot simply send a technician to replace a broken hard drive. Every component inside this vessel must be designed for a 5-year lifespan without any human intervention. The container is filled with dry nitrogen to prevent corrosion and minimize fire risks. By placing data centers near coastal cities, Microsoft also reduces latency for millions of users. It is a bold experiment that turns the cold, dark deep into a vital asset for the digital age. As the world shifts toward electric vehicles, the demand for cobalt, nickel, and manganese has reached critical levels. Allsea's Hidden Gem project targets these minerals on the abyssal plain, 4 kilometers below the surface. This collection test utilizes a specialized subsea crawler designed to navigate the soft, silty floor of the Clarion-Clipperton zone. The machine must pick up polymetallic nodules, small potato-sized rocks rich in rare metals, while minimizing the disturbance to the surrounding sediment. The primary technical challenge is the vertical transport system. How do you move thousands of tons of rock from the seabed to a surface ship without clogging the pipes? Allseas uses a high-capacity riser system and airlift technology to pump the nodules to the surface. Every movement of the crawler is monitored to track its environmental footprint, as the deep sea is one of the world's most fragile ecosystems. This project represents the next gold rush, where extreme logistics and environmental engineering must find a delicate balance to secure the future of global battery production. Aging infrastructure is a silent threat to global energy security. The Tetney Sea Line Replacement Project demonstrates the complexity of upgrading essential pipelines without interrupting service. The project involves replacing a decades-old oil line that connects a single-point mooring to an onshore refinery. The hardest part of this replacement is the tie-in process. Divers and ROV teams must work in the murky, high-current waters of the Humber Estuary to disconnect the old pipe and secure the new one. The installation uses a specialized pipe pulling method. A powerful winch on the beach pulls the new, heavy-walled steel line into a pre-dredged trench. Precision is everything. If the line is pulled too fast, it risks damage to the external coating, leading to premature corrosion. Once in place, the pipe must be pigged, a process where an internal cleaning and inspection tool is run through the entire length to ensure there are no obstructions or weld defects. This project highlights a shift in focus for offshore engineering. We are no longer just building new networks. We are performing surgical repairs on the existing foundations of our industrial world. It is a grueling, invisible task that ensures millions of liters of oil reach their destinations safely every single day. In Nigeria, the John Denul Group has undertaken a massive dredging and reclamation project to support the Dangote refinery, one of the largest industrial hubs in Africa. The challenge here is the geology of the coastline. To create a stable platform for heavy industry, engineers must move millions of cubic meters of sand to reclaim land from the sea. This is not just moving dirt, it is a complex soil improvement project. The process utilizes high-capacity trailing suction hopper dredgers. These vessels vacuum sand from the seabed and discharge it onto the site through massive pipelines. Once the sand is deposited, it must be compacted using vibro-compaction to ensure it can support the weight of giant oil tanks and heavy machinery. If the compaction isn't perfect, the ground will liquefy during an earthquake or shift under the weight of the refinery. The project also involves the installation of a massive single-point mooring system, allowing ultra-large crude carriers to unload their cargo miles from the shallow coastline. This requires the installation of heavy subsea pipes and anchor chains, creating a deep-water port where none existed before. The Dangote project is a prime example of how extreme logistics can transform a nation's industrial landscape. By reclaiming land and building deep-water access, engineers are creating a permanent foundation for economic growth in one of the world's most rapidly developing regions. Sometimes the most critical logistics happen between two moving targets. A ship-to-ship transfer is a high-stakes operation where two massive vessels, often carrying flammable hydrocarbons, must dock while at sea. The primary problem is motion. Without the stability of a fixed pier, the ships must use specialized fenders to absorb the impact of waves and prevent hull damage. The connection involves the transfer of flexible hoses, which are lifted by cranes and secured by specialized mooring teams. During the entire transfer, both vessels must maintain a constant speed and heading, often using a single pilot to coordinate both bridges. If the weather turns, the operation must be aborted instantly using emergency release couplings. It is a masterclass in maritime coordination, allowing global energy markets to stay flexible by moving cargo without ever entering a port. This operation represents the final, vital link in the offshore supply chain. The Dan Bravo complex in the Danish North Sea is a testament to the longevity of offshore engineering. First established in the 1970s, this massive hub has undergone decades of upgrades to stay operational. We see the complex network of interconnected platforms, each serving a specific function, from drilling and production to living quarters for hundreds of workers. The hardest part of maintaining a legacy complex like this is managing the integrity of old structures while integrating modern digital controls. Every bridge and walkway between these platforms is a lifeline, and every underwater leg is a target for corrosion. Dan Bravo shows us that the subsea frontier isn't just about the newest technology. It's about the relentless human effort required to keep the world's most complex machines running for generations. Even the most heavily armored cables are not invincible. A stray ship anchor or shifting tectonic plates can snap a subsea lifeline in an instant, plunging entire communities into darkness. The repair of the Aran Islands cable demonstrates the surgical precision required to fix a problem miles beneath the waves. The process begins with fault locating, using electrical pulses to find the exact breakpoint. Once identified, a repair vessel must grapple the broken ends and bring them to the surface. This is a delicate operation. The cable must be handled with extreme care to avoid further damage to the internal fiber optics. On deck, specialized jointers work in a clean room environment to splice the tiny glass fibers and re-insulate the power cores. It is a race against the tide and weather, proving that in offshore engineering, the ability to repair is just as vital as the ability to build. What happens when a subsea cable reaches the end of its 50-year lifespan? It doesn't just become ocean waste. High-voltage cables are gold mines of high-purity copper, lead, and steel. The recycling process is a masterclass in industrial separation. First, the heavy outer armoring is stripped away using mechanical crushers. The lead sheathing is melted down for reuse, while the copper core is granulated into fine particles. This closed-loop system is essential for the sustainability of the energy transition. By recovering these materials, we reduce the need for destructive land-based mining and lower the overall carbon footprint of future offshore projects. This is the final stage of a cable's journey, moving from the dark silence of the ocean floor back into the industrial cycle to be reborn as a part of a new, high-tech system. To look at a modern cable-laying fleet is to see the pinnacle of maritime evolution. These vessels are more than just transport ships. They are floating command centers, heavy factories, and deep-sea research labs all in one. Equipped with dual carousel systems, they can carry enough cable to link entire nations in a single voyage. Their advanced dynamic positioning allows them to stay perfectly stationary in North Sea gales, while their integrated ROV hangars ensure that human eyes are always on the seabed. The primary problem these vessels solve is the scale of human ambition. As we build larger wind farms and deeper data networks, the demand for ships that can handle heavier loads and more complex installations grows. We see the integration of hybrid propulsion systems and automated cable handling, reducing the risk to crews while increasing the speed of global connectivity. These ships are the unsung heroes of the modern world, working in the most hostile environments to ensure that energy and information flow without interruption. They represent a legacy of engineering that refuses to be limited by the ocean's depth. As we look to the future, these vessels will continue to push further, laying the foundation for a planet that is more connected, more sustainable, and more resilient than ever before. This is the true legacy of offshore engineering, a world built on invisible, unbreakable connections.